Hey everyone, and welcome to this AI.NET Mind Explainer. Today, we're going to unravel the crucial, completely invisible network processes that happen the exact moment a device connects to a network. Seriously, whether you're a total networking beginner, maybe you're studying for your CCNA, or you're already working in IT support, understanding these core protocols is absolutely fundamental. We're going to trace the life of a single packet as a laptop joins a Wi-Fi network and attempts to open a website. It's going to be a fun ride.
Think about this. You connect your laptop to Wi-Fi and type a website name. Boom! But before that web page even starts loading, DHCP, ARP, and DNS have already done three completely different jobs. It all happens in literally milliseconds, but the sheer complexity of what's occurring behind the scenes, it's kind of staggering. Your device has to get an identity, it has to figure out how to speak to its local neighbors, and it has to translate human language into computer coordinates, all in the blink of an eye.
So here's our roadmap for today. We'll start with DHCP configuration, then move to finding the local MAC address with ARP, followed by DNS resolution. After that, we'll map all this onto an end-to-end timeline, and we'll wrap the whole shebang up with some troubleshooting and a quick CCNA pop quiz.
All right, let's dive right into step one of our journey. DHCP, configure the client.
So meet DHCP, the Dynamic Host Configuration Protocol. Think about what happens when you walk into a local coffee shop with your phone or tablet. You don't walk up to the barista and say, "Hey, can I get a latte and what's my subnet mask?" Right? You don't manually type it into your settings. Manual addressing simply does not scale in modern enterprise or wireless networks. It'd be a nightmare. DHCP is the automated system that dynamically discovers and leases an IP address to your device. It saves IT staff from administrative headaches and keeps users from accidentally duplicating IP addresses.
Now, this entire exchange happens through a really elegant four-step dance, famously known by the acronym DORA, DORA. First up, discover. Your laptop basically shouts a broadcast message to the entire local network asking, "Hey, are there any DHCP servers out there?" Second, offer. A listening DHCP server replies with a proposed IP address and configuration. Third, request. Your client broadcasts again, officially requesting to use that specific offered IP address. And this actually does double duty because it implicitly declines any other offers it might have gotten from competing servers. Finally, acknowledge, or ACK. The server sends a confirmation message, locking in the lease.
But listen, DHCP does so much more than just hand out an IP address. It provides your client with a complete starter pack. It gives you a subnet mask so your device understands the network size, the default gateway so it knows how to actually leave the local network, and the DNS server address so it can resolve website names later on. It's also really important to grasp the lease concept here. These IP assignments are temporary. It's like a rental, allowing the server to reclaim and reuse addresses when a device disconnects. Oh, and if your DHCP server is located on a totally different subnet, routers use a neat feature called DHCP relay, often configured with an IP helper address command to forward those broadcasts across. All of this magic happens over UDP port 67 for the server and 68 for the client.
Moving right along, let's look at protocol number 2, ARP, Find Local MAC.
So here is a super crucial concept. We have to clear up the difference between two very specific types of addresses. You've got an IP4 address, right, which is logical. It exists at layer 3 of the OSI model, and it's used for end-to-end routing across the entire globe. Think of it like a mailing address. But then you have a MAC address. This is a physical hardware address permanently burned into your laptop's network card. It operates at layer 2, specifically for things like Ethernet and Wi-Fi, and it is strictly used to deliver frames from one device to the very next physical device within the same local broadcast domain. To actually send data, your laptop has to map that logical IP to a physical MAC address, and making that mapping happen is the exact job of the Address Resolution Protocol, or ARP. When your laptop wants to talk to a local device, it first checks its own ARP cache, basically its internal short-term memory, to see if it already knows the MAC address. If it doesn't, it sends out a massive broadcast ARP request to the entire local network, essentially shouting to the room, "Who has this IP address? Tell me your MAC address." Every single device hears this shout, but only the specific device holding that IP address will respond. It sends a unicast ARP reply directly back saying, "Yep, I have this IP and here's my MAC." Okay, pay super close attention to this next point because it is a massive stumbling block for beginners. ARP is strictly local. Broadcasts do not normally cross routers.
If your laptop wants to load a website hosted on a server in, say, a completely different country, it does not send an ARP request for that remote server's MAC address. I mean, it couldn't even if it tried. Instead, your laptop looks at its subnet mask, recognizes the destination is remote, and it sends an ARP request for its default gateway's MAC address. The default gateway, which is just your local router, will take the packet and handle the rest of the journey. All right, we're fully configured, and we know how to reach our local router to access the internet. Now for the final piece of the puzzle, DNS, resolve the name. Let's be honest, humans are terrible at remembering random strings of numbers. That's exactly why we don't type 142.250.190.46 to search the web. We just type a domain name. The domain name system, or DNS, is the system that translates these human-readable host names into the IP addresses that computers actually need to route traffic. And a quick technical note. While it heavily uses UDP port 53 for standard queries, TCP port 53 is absolutely used as well, particularly for things like zone transfers or when responses are just too large for a standard UDP datagram.
So how does this actually work globally? Well, it builds an incredible hierarchy. When you type that website name, your laptop doesn't usually do all the heavy lifting itself to scour the internet. It simply asks its configured recursive resolver, which, remember, was handed to it earlier by DHCP. This resolver acts as your personal agent. It queries the global root servers, which point it down to the top-level domain servers, like the .com or .org servers, which finally point it to the authoritative server. That's the server that actually holds the specific IP address for the website you want. That authoritative answer is passed back down the chain to your resolver, and finally handed right back to your client.
Now, the data returned by DNS comes in a few specific record types. For our IPv4 network example, we're looking for an A record, which maps a name to an IPv4 address. If we were using IPv6, it would be a quad A record. You might also run into CNAMEs, which act as aliases, MX records used for routing emails, and NS records for identifying the name servers themselves. And to keep the internet from literally collapsing under the weight of constant queries, DNS heavily relies on caching. This is governed by a TTL, or time to live. It's basically an expiration date that tells your computer exactly how many seconds it's allowed to remember this IP address before it has to go ask the server all over again.
Okay, we've explored the 3 distinct jobs. Now, let's watch them happen in real time in Section 4, the end-to-end timeline.
This is where it gets really cool. Let's combine all 3 protocols into a single, seamless story. At 0 milliseconds, the physical connection happens. Your laptop joins the Wi-Fi. By 10 milliseconds, that DORA process completes. DHCP provides the IP, mask, gateway, and DNS servers. At 20 milliseconds, you type a website. The laptop checks its subnet mask and realizes, hey, this destination is remote. By 30 milliseconds, the laptop uses ARP to find the local MAC address of its default gateway so it can actually send traffic off network. At 40 milliseconds, it shoots a DNS query over to its resolver to find the website's IP address. And finally, by 50 milliseconds, having an IP identity, a local MAC destination, and a remote IP destination, the device actually begins downloading the web page. All of that in a fraction of a second.
Understanding that exact timeline is your superpower for fixing things. Let's transition to Section 5, Troubleshooting and CCNA Quiz.
First up, let's clear the air on some super common beginner misconceptions. Remember, DHCP configures you, it does not resolve names. And it supplies way more than just an IP address. ARP bridges logical and physical addresses locally, it does not resolve domains, and again, its broadcasts do not cross routers. That remote destination's MAC address, it is never needed by your laptop. Finally, DNS translates names, it absolutely does not assign client IPs, and it's a massive distributed hierarchy, not just one single giant global server.
When things break out in the real world, you can actually map the symptom directly back to the protocol. If a user complains they have no internet, and you see they have a completely blank or auto-configured IPv4 address, you've got a DHCP problem. Maybe it's a rogue server or a missing IP helper address. Now, if the user can ping 8.8.8 successfully, meaning their actual IP connectivity works, but they cannot load a website by name, you are definitely looking at a DNS problem. And if they have a valid IP but simply cannot reach or even resolve the MAC of their default gateway, you're looking at an ARP or local Layer 2 LAN issue. To actually verify these network states, here are your bread and butter commands. On Windows, ipconfig/all will show you your DHCP lease details and your DNS servers. ARP-A prints your local ARP cache, and NSLOOKUP lets you manually query DNS. If you're on Cisco routers and switches, you'll rely heavily on show IP ARP to view the ARP table,
show IP interface brief to verify physical status, and show IP route to ensure your Layer 3 paths exist. Just a quick heads up, platform-specific DHCP verification commands can vary wildly between vendors, so always check your documentation.
All right, time for a quick, rapid-fire CCNA quiz. Let's see if you can beat me to the answers. Number 1, which protocol automatically provides a client IP? That's DHCP. Number 2, what are the 4 DORA messages? Discover, offer, request, acknowledge. Number 3, which protocol maps IPv4 to MAC? That is ARP. Number 4, for a remote destination, whose MAC does the source need? The default gateway. Number 5, which protocol translates a website name to an IP? DNS. And finally, number 6, which server holds the actual final DNS data for a domain? The authoritative server. How'd you do?
To lock this in your brain forever, just remember this little cheat code. DHCP means configure me, ARP means find locally, and DNS means find by name. Say it with me. DHCP configures you, ARP finds your local next hop, DNS finds destinations by name. If this explainer helped clear things up for you, please hit that like button, comment down below on which networking topic you want us to explain next, and subscribe to AI NetMind for more AI, networking, cloud, and cybersecurity content. But before you go, I want you to think about this final question. If ARP only works locally, how does a hacker on the exact opposite side of the globe manage to intercept your traffic? Keep learning, and we'll explore exactly how that works in the next explainer. See you then.